Let's remind ourselves what we need to have to do query optimization. We start with the given of a closed set of operators. This includes relational operators that take a table in and a table out, and particularly the physical implementations of those operators. So things like hash joins and sort merge joins and index scans. Also physical implementations of some operators that aren't in the relational algebra that we might want to use in our queries, including sorting, for example. All right, given that closed set of operators, we have a plan space, which is all of the possible query plans that produce the correct answer to a query. And that space is defined by the relational equivalences and then the physical equivalences of the implementations of those relational operators. The second thing we need, which we haven't talked about yet, is cost estimation. We need to figure out what the cost is of a potential plan we want to use. So we're going to need some formulas for the cost of our operators. We're also going to need estimation of the size of the data that goes into these operators. And that in turn is going to be based on catalog information about the base tables, which is going to describe the size of the stored tables. And then an estimation problem we're going to call selectivity estimation, or the textbook calls it reduction factor estimation. And that's going to help us determine the sizes of inputs to downstream operators. Finally, we're going to need a search algorithm that's going to sift through this entire plan space and find us the lowest cost option. So in the previous lecture, we looked at issue number 1, and in today's lecture, we're going to look deeply into issues number 2 and number 3. Reminder, in this context, we're talking about the System R, or Selinger optimizer, based on the famous paper written by Pat Selinger et al. In 1979 at IBM Research. It's a remarkably comprehensive framework. Some people refer to that as the Bible of query optimization. Many of the details, though, in that paper were a first cut. It was really the first paper on the topic a long time back. And so there have been many refinements over the years, and we'll see some of those refinements in our lecture today. But I want you to know this remains an ongoing area of research. We're still writing papers about query optimization and how to make it better on pretty much all 3 of the axes we described on the previous slide. The big picture of the System R optimizer, well, it works pretty well, but only up to about 10 to 15 joins. And when you think about that, that's probably the biggest SQL query you can imagine. It's weird to think about writing a query with more than 15 tables in it, but it does happen, and it often happens from tools, from visual tools that generate queries. And then you get very, very large SQL queries. So at that point, the System R optimizer really can't be used, and you have to fall back to heuristics. But today we'll focus on the case of when we can use the System R optimizer, which is kind of the meat and potatoes workloads you get in databases most of the time. The plan space is, even for these queries, pretty much too big to search exhaustively, and we need to prune it. Now, the first thing we can point out is there's an algorithmic insight that's key to the System R paper, which says that many plans could have the same overpriced subtree in them. There might be a subplan in the space that's just really, really expensive, and there's a better way to do that subplan. So any tree that contains that subplan is itself a bad plan. So we're going to ignore any plan that contains an overpriced subplan. All right, and then on top of that algorithmic insight, which is just a true statement, there's a bunch of heuristics, which are heuristics. So sometimes they're a good idea, and sometimes it turns out they're not. But they are common, and they work most of the time. So one common heuristic is to look only at left deep plans, and we'll talk about what that means today. Another is to look only at Cartesian products, as we talked about last time. And we'll show you today exactly how that fits into the search strategy. Secondarily, we need to look at cost estimation. We'll spend a bunch of time on this today. It's very inexact in that System R optimizer in particular. The original paper is quite inexact. It works okay in practice, though. It often allows us to find pretty good plans and avoid really bad ones. So it doesn't have to be perfect. The statistics in system catalogs are usually fine. They're used to estimate the sizes of the base tables and therefore the costs of operations on those base tables. The cost estimation in the System R paper considered both CPU and I/O costs. Today, for simplicity, we'll mostly talk about I/O costs, and CPU costs are usually just a small fraction on top of that. And I will say that System R's schemes for cost estimation have been improved over time, and today we'll look at one improvement along those lines, which is in terms of using histograms instead of just using simple statistics. And you'll see what I mean when we get there. The final component is a search algorithm, and System R developed a dynamic programming-based search algorithm for doing query optimization. You've probably learned dynamic programming before. You may not have, in which case you'll learn it here, and that's fine. I'll point out that dynamic programming is a typical technique used in computer science for optimization problems with subcomponents of the sort that we're going to do here. It's widely used in modern AI, and yet another connection, I guess, between the fact that query optimizers, although developed in the database community, are an example of sort of automated, intelligent generation of code.